So my name is Aarav, and my friend Anika, and we're doing the pallet cartonization project and for Perseus. And the goal of this project, overall, is to minimize the height of a pallet for the most cost efficient way. So as I said before, my name is Aarav Srivastava. I'm a rising freshman in high school who lives in Texas. I love learning about computer science and math, and I'm also very passionate about swimming.
Everyone, my name is Anika Kumar. I'm a rising senior in high school in the Bay Area. Ever since I was a kid, I've always loved to code, engineer, and delve deep into math, even through math. But I also really like applied math. So I do robotics. I'm the programming captain at my robotics team. And I'm also president of the girls technology club at my school. And I'm super excited by machine learning, AI, and data science driven problems, and looking forward to pursuing this when I get older and applying them to problems for social good. So, what Perseus does is optimizes the packing process to be the most cost effective.
Perseus optimizes the packing process to be the most cost efficient as possible. And they can also alter the algorithm to be specialized for different companies' needs, which is what we're doing in our project. Uh, this can help within the warehouse for packing different items by providing the exact layout of how the items will go into boxes with 3D visualizations and labels.
Yeah, and so building upon that, our specific solution or customer request involved a pallet. And a pallet is a portable transportation structure that's used a lot for shipping and packing. It's looks like as you can see here. And unlike boxes, they don't have a fixed height. Their height dictates their cost. So you stack boxes on top of the pallet, and then their height is just the tallest, is just the height of the boxes. And so this is unlike a box, which has a fixed height. Um, and it's extremely widely used. There's 1.9 billion pallets in use in the US each year. And so, building upon that, our specific customer was Titus Wilson from IQ Pack. And the overarching goal of this project was to build an API that allows shippers to build pallets that would be transported by trucks. Um, and so, the requirements for this was to make each pallet as short as possible because taller pallets are more expensive. And so, yeah, as mentioned, unlike the cartonization problem that Perseus has with packing items into boxes, we had to repurpose that API to pack boxes into pallets. And the biggest constraint of this project was definitely the time. We had 8 weeks, so we had to call the existing API with using some high optimized logic. We didn't have time to to create an algorithm that plays the three Tetris, as Thomas likes to refer to it. Again, we needed to uh, figure out how to repurpose the generic cartonization algorithm for the palette application. So from the website, this is essentially a pipeline. From the website, we would have gotten the palette length and width, which we're assuming is fixed, as well as the box sizes and dimensions, and then also the cost per height. So for every additional inch of the palette height increasing, the cost increasing by a fixed amount. So that means like if we have a 20-inch pallet, that's the same as two 10-inch pallets. That's kind of an assumption we're making. And we're taking all that data and transforming it into a cartonization request using some logic that we'll explain later, that we then send to the generic cartonization API that Perseus has.
We had two solutions, but this is the first solution and it's not fully completed. And the way the first solution works is you pack one unit into each pallet until the amount of pallets that we think there are going to be is filled. After that, you assign each item to its own pallet using an index, which is a array that we have with all the pallets and all the items in each pallet. Once we assign an item to each pallet, uh, then you continue packing the remaining items in each pallet by looking at the pallet with the least amount of volume in total, uh, and then you put the item there, assuming it's the best place to put it. And so, as you can see here, um, we loop in the first part, we loop through each item in the list, and each item has fields like quantity and dimensions. As long as we haven't packed more items than the estimate allows, meaning the amount of pallets that we think there are going to be allows, then we start with simple distribution where each item gets its own pallet, meaning one item per pallet. For the given quantity, we add one item at a time, and each item is packed on a separate pallet using its index. We increment the packed counter after each addition uh, until we reach the estimated pallet limit, until we reach the estimated, wait, no, we increment the packed counter until we reach the amount where it's full. Once there's an item in each pallet, then we go to phase two, and then there we loop through the function and add a item to the pallet with the least amount of volume used um until all the items are gone and all the pallets are full.
Yeah, so another algorithm we also attempted was the recursive algorithm, which was more fluid and less approximation than the solution earlier, which estimated the number of pallets. So basically, as mentioned, we usually data from the customer, and our goal is to send a request to the existing Proteus cart organization API using some logic, which is volume logic, and I'll explain that in a second. And we're essentially trying to find the minimum height possible that we can fit all pallets in all boxes in one, or boxes or items in one pallet, because this would minimize the height in theory. So the first thing we do is find a total volume of all the items. So we sum each of the individual items volumes together. And then we divide by the pallet base area um, to find the absolute minimum possible height that a pallet could be. We multiply by some buffer. This field was initialized when we created an object that the generate request object. But essentially it's a parameter that we specify that allows there to be, in case um, we want to circumvent against the possibility that the geometry doesn't work with having this very theoretical calculation of volume divided by area. So although that could theoretically fit all the items, it's very likely that the configuration of the items doesn't fit exactly. So that's what that buffer is for. And then also we want to make sure that it's physically possible to fit all the items into the pallet. And so, for example, if you had a 2 by 2 by 2 meter cubed box, and you also had a 4 by 4 by 0.5 meter cubed pallet, you wouldn't be able to fit, despite them having the same volume, you wouldn't be able to fit the item into the box because 2 is greater than 0.5. And so this is giving us that absolute minimum height using some minimax logic from the items. And so we check to make sure that the pallet height is less than that. And yeah, so we send this request with these palette specifications, notably height, to the Perseus API, but we end up actually having to do this recursively. And so this method basically returns a request given a list of items, but it's still possible that given all the like measures taken to prevent against the geometry not working, it still doesn't work. And so we end up calling this method recursively. Um, so this recursive palette cartonization essentially takes in first uh, the items that we've already packed, which is initialized to, or the pallets that we've already packed initialized to just an empty list. And then items that we still need to be packed initialized to the initial item list that the customer gives us. And then these dimensions, fixed dimensions, and cost per inch of height, as well as the Perseus API client and then the request generator, which was the object of this method earlier. So the base case of the recursion is that all of our items are packed. That is the length of our to be packed list is 0. And in that case, we just return the already packed list that we've created. And otherwise, we have to resend a request to the Perseus API because we still have items to be packed. So we send a request here. We do some error handling, and then we essentially parse through the response to get the very first pallet that the API returns. And so essentially this is because if you had 10 pallets, and we calculated the height of uh, the height of the pallet to hold those 10 items to be, or sorry, 10 items. We calculated the height of those 10 items to be something. And the Perseus API ended up actually splitting those two items, those 10 items into 9 and 1 items. So the 9 items pallet would have a much larger height than the 1 item pallet. And so that means that we need to recall the volume logic with the second item, with the 1 item, to make sure that we're not adding unnecessary height to the calculation. So yeah, so essentially that's what we're doing here. We're taking the very first box that the Perseus API returns, and then um, we're using the items left in the second, third, and fourth, or etc. pallets from the response uh, to recall with the volume logic and recalculate the height. And so we've updated the list here and we're redoing the recursion. And so that was a lot of code, but I think we all want to see it in action. So here's a quick demo of our work. Um, so in our post API tests, we have this theoretical simulated data from the user. In reality, this would be from a website. And
Anika,
so, yeah.
think
Oh,
you're sharing wrong window.
sorry. Okay. Yeah, so this would be the simulated data from the user. And so we have an items list that they give us. So let's say they gave us one big box, one medium box, and 2 small boxes just to start. Or sorry, we have to review this. And then uh, I think I'll have to share my entire screen. So this is the solution for that one. So we have one big box, one medium box, and 2 small boxes. And so in this case, they were able to fit in 1 pallet. If we were to call the API again using a different number of boxes. So let's say we had 3 big boxes, 4 medium boxes, and 4 small boxes. This might need to split the items into 2 separate pallets. Yeah, so if I click this, so this is the first pallet that we've optimized for height, and then this is the second. Okay, so some key takeaways that we've got from this experience. We got real technical experience with Flask and data wrangling, which is much different than theoretical and research that we've had experience with before. We learned a lot about like Flask, as mentioned, so post versus get requests, integrating APIs, like the Perseus API with ours, and then also AWS Marketplace, which is where we run our server on.
We also learned about the intricacies of the shipping process, as well as working on GitHub with a teammate, because there's a lot of different stuff you have to worry about whenever you're working with a teammate as compared to by yourself. And we also got to meet a lot of other talented people and got the opportunity to work one-on-one with Thomas, which led to amazing first experience in a startup setting.
Right, the quorum is open for any questions for Anika and Aarav. I have a question. Given what you guys have built so far, for example, in the recursive method, right? I could see how sometimes you throw it a bunch of stuff. It sometimes builds a palette that's kind of high and kind of short. What do you think, which to me seems like could be improved intuitively, like instead of having like a tall palette and a kind of short palette, having 2 sort of same height palettes. I'm wondering, have you guys thought about that? If so, what like a possible like next sort of solution would be on the roadmap if you like continue the internship?
I think that I'm not sure about the recursive one, but I think that the first solution that we're working on, I think that will solve that problem because we're adding an item to each pallet one at a time. So in the end, it should be around the same height, even if it differs a little bit.
Yeah, I think that's exactly right. So we have like an estimated number of pallets for that solution, and for each estimated number of for each pallet in that we have a fixed height. So in that solution, you have like very rigid. Each pallet that we return has the same height, even though, and then you add items corresponding to the volume that is currently used. Yeah, so I think that would solve that issue. We're just trying to debug that solution right now.
Sounds great. Any other questions?
So this
Yeah.
is Nitin. My name is Nitin. I have a kind of question. So how can one tell that the palette is optimized? Like, how can we ensure that? Like, what other way to kind of uh, what I'm leaning towards is like, did the team look at like the physical boxes, just real life, and kind of say that, hey, this is the most optimal way, and there's no way anybody else can arrange it, which is more efficient than what the program is telling us.
I'll take this one. What you're referring to is something that is super important, super interesting, and super hard. Which is, all of these problems, in the like a computer science terminology are NP complete. So like perfect solutions, for big instances of these problems, like once you're packing 50 boxes somewhere, like no one even knows what a perfect solution looks like, right? It's all about uh it's all about can you get good enough solutions fast enough? And like good enough generally is measured. You look at customers' historical data, how they packed and how much they spent. Then you run it through your algo and you see, okay, given the rules for pricing and everything, this is how the simulated, instance would cost. And, if there's a good diff, then we'd say it's optimal. It's like we're getting closer to an optimum. But like true optimums in these like in these com in these large combinatorial instances are like no one knows like if I give you 100 boxes and build pallets and these are the pricing functions of the pallets, no one really knows what the optimal looks like,
Oh, thank you. Yeah. Okay. No, understood. Yeah.
Great
Yeah, it's a very
question
hard
though.
problem. It's a very hard problem though, and I don't think no one here would actually expect interns who are yet to go to university to actually solve something like this. I have a question, and it's going to be aimed towards both of you. It's a hypothetical question. Given what you've learned, what you've experienced during this internship, you've tried not only just algorithmization, but also you tried, working on the back end and even the front end. Uh, was there like a specific area that you really loved? And if given the option to like continue the internship, what would be the area that you would like to develop further in, if you have such an idea?
Uh, for me, I would just like to continue like coding the algorithms. I liked coding the algorithms uh, a lot more than all of the other stuff.
Yeah, I agree. I think like coming up with like a novel solution to like a problem that hasn't been solved, or a solution that like yeah, a solution that it doesn't already exist, like instead of like fine-tuning an existing thing, making something new is definitely fun. But I think if I was to continue the internship, I'd like to like work on this project more and like see it into development and actually like hand it to the customer. That would be awesome. Um, yeah.
Okay, cool. Thank you.
Got a question for you. So the dimensions that you guys put in there, are they fixed orientations or does the program have the ability to look at possibly rotating boxes or turning them on their sides in order to really maximize that density.
Yeah, so the existing Perseus API like rotates, does all the rotations and translations necessary in order to get it to fit into a pallet. Yeah.
Okay. And can you pass it some sort of parameter that says, hey, I want to fix the orientation so that these only stay upright, or will it by default want to orient it
So
however it wants to get the density?
I
That's
will
what
answer
the
that.
okay.
I will answer that. I will answer that. This functionality wasn't I think, available at the time as the interns were working on this, but the functionality is available now. So I assume that if given the choice, it would actually be implemented. But correct me if I'm wrong.
Yeah, and by the way, for context, Dustin is a is working directly with us. He's a prospective customer who's been like we've been piloting some stuff in his warehouse. So like this is a real like industry person who moves pallets day in and day out. And so Dustin, thank you so much for taking the time early in the morning on a Friday here. I mean,
No, for sure. It's very cool to see you guys are doing some pretty cool stuff out there. It's awesome to get to witness some of that.
yeah, man, if you like, if you need if you need an algorithm for packing pallets, man, like we got you set up here with Anika and Aarav.
Seems like it.
One kind of as a generic question. So, what were the big like one? What is one aha moment for each one of you while you were working on this project?
For me personally, I think it was the time when I realized we could do recursion. Because like I was at first like when I gave this problem, I was very like stumped for sure because it was how are we supposed to optimize height if we can't create a new algorithm altogether? So I think like when I finally realized that we could do this method of recursion, that was the aha moment of the project.
For me, it was whenever I realized that we could, instead of like adding items to one palette and then going on to the next palette, we could instead loop through the palettes and add an item to each palette individually.
Thank you.
Alrighty, guys, I'm super happy the audience woke up and started bombarding us with questions. Nothing more fun than having an engaged audience. So